Thanks for coming to this second tutorial. I'm going to talk about room acoustic simulation, and kind of in contrast to Jean-Marc's talk, it's mostly going to be about the physical reverb stuff that he kind of mentioned in passing. Here's a quick outline of the talk. So I'll just introduce the problem and context, go over some basics of room acoustics, mostly from the point of view of wave theory. It's kind of the most general way to describe room acoustics, and ultimately what we're trying to simulate, whether it's directly from waves or from some other abstraction. And then I'll talk about geometric acoustic simulation, so that's the most popular family of room acoustic simulation methods, followed by wave simulation methods, which essentially aim to simulate the 3D wave equation. And then I'll go over some recent developments in terms of finite difference time domain methods, which is a popular wave-based method, and one that we focus on quite a lot in the acoustics group here. And then hopefully I'll have time for conclusions and questions. So the general problem here is, how do we derive sound from a computer model of a 3D room? So here we have a concert hall model, and we want to derive some audio that pertains to this space, including some of the acoustics. Often what's desired is a room impulse response, so that's the sound at some point in the room in response to an impulsive source at some other point in the room. And then you could take that. So here, this is an impulse response. If you've never heard one before, we'll listen to one right now. So it's a bit quiet, sorry. So what you can do with that is take a some dry audio.
Techniques for acoustic simulations.
And then convolve the two to get a reverb effect.
Techniques for acoustic simulations.
Okay. And the applications of room acoustic simulation are, of course, digital reverb. It's also used in architectural acoustics. They use these simulations to help design concert halls and other types of spaces where acoustics are key. And it's becoming increasingly important, as we saw in the last talk, in video games and virtual reality applications, where it's an integral part of what people are calling 3D audio. So I'll just jump into a quick example of wave propagation in a room. Here's a really simple example. I'm going to cheat a bit and consider a room that's confined to 2 spatial dimensions, which changes the nature of wave propagation somewhat, but nothing too important for the purposes of this illustration. So we have a sound source at that point marked X, and sound waves propagating through the room, bouncing off the walls. Okay, so we'll look at this a bit more closely. So we have our source position, and then we'll fix 2 arbitrary receiver positions. So we can start to describe the sound propagation paths between the sources and receivers. So first of all, we have obviously the direct sound. It's a straight line between the source and receiver. And indeed, you can see that the wave travels, you have a wave front traveling normal to that line. You also have specular reflections, where the angle of incidence the wave makes with the wall is equal to the angle of reflection. So if you follow along this wave, you'll see it follows those 2 paths to reach the first receiver. So that's essentially Fermat's principle. It describes sound propagating along straight lines, the law of reflection there. And in a nutshell, that's kind of geometrical acoustics. If we consider the other receiver in this room, we see that the first sound event is actually not due to any of those geometric laws, but more it's a sound wave bending around the corner. So that's obviously known as diffraction. And as the sound wave bends around the corner, you can see that it actually scatters a bit, and it sends out other waves, which will then bounce around the room and create other specular reflections and other diffracted waves. And then finally, if we look at the right, we have a kind of rough wall. It's just a collection of flat portions. And when the sound hits this, we call it a diffuse reflection, because it scatters the sound. It kind of diffuses the sound through the room. But really, it's just a collection. It's just a combination of specular reflections and diffraction. So what you have is kind of the sound waves kind of bending around these corners on a micro scale. But macroscopically, we call it diffuse reflections. So I'll focus a bit more on diffraction, because it's really the key concept that differentiates geometrical acoustics from wave-based acoustics. So in the context of 3D room acoustics, you have a few criteria for determining when and where diffraction will take place. The first criteria has to do with the interior angles between walls. So essentially, any interior angle which is not equal to pi over n radians, where n is an integer, you're going to have some diffraction event. So in this room, we have 90-degree angles, a pi over 3 60-degree angle here, and that one's not pi over n. And if we watch what happens, we see right here, this is a diffracted wave. It's centered around that corner, so that's how you know it's diffraction. If you look at the other corner, you don't have a kind of circular wave centered around the corner. And if you follow along, you'll see these two corners don't generate diffraction, but every time a wave hits this corner, you have diffraction. So, and it kind of follows that anytime you would have a curved surface, you would have diffraction as well. The other type of diffraction you can get in room acoustics is at material discontinuities. So in this room, we have 90-degree angles everywhere. We don't expect diffraction from the corners, but I've set it up so that we have rigid walls, and here this section is partially absorbing. And if you watch what happens, you'll see diffracted waves happening at that interface. So that's the other kind of diffraction you can get in room acoustics. Okay, so that brings me to geometric acoustic simulations. So I'll start with classic geometrical acoustics and then move on to more modern developments. So classic, or the purest form of geometrical acoustics, is just based on Fermat's principle, the idea that waves travel along straight lines and reflections follow the law of reflection, so the angle of incidence equaling the angle of reflection. And this precludes any form of diffraction. So I'll talk about extensions to add in diffraction later. So in general, this is going to be a high-frequency approximation because in general rooms you will have diffraction, but in high frequencies it's going to be less pronounced. So here we have two plane waves passing through an opening, and you can see that the waves bend a bit more in the low-frequency case than the high-frequency case. So another way to put this is for this approximation to be valid, you need the wavelengths of interest to be small with respect to the surfaces in the room. And this doesn't rely on any diffuse field assumptions for now, okay? So the main task in any kind of geometric acoustic simulation is simply to find sound propagation paths between the source and receivers, or sources and receivers, in order to build up an impulse response. So here we have a few sound propagation paths we've identified, and you can turn that into an impulse response simply by taking the length of each path, or the distance traveled by each sound wave, and dividing by the speed of sound to get a time of arrival, which you can then discretize according to your audio rate. You can interpret that sound event as an impulse, so you discretize that as with a Kronecker delta or a sinc function. You place it in your impulse response, and then you scale it according to 1 over the distance. So this is due to the Green's function in 3D for the 3D wave equation. And you also scale it according to all the reflection coefficients of the walls. So you can calculate the reflection coefficient from an admittance or an impedance for the wall. That could be frequency dependent as well. For now, we're just assuming it's frequency independent. And the main techniques for calculating these sound propagation paths are the image source method and ray tracing. So I'll go over these next, starting with image source. So you probably know this, the image source method for a box-shaped room. It's quite simple to do in a box. I'm going to consider the arbitrary shaped room. It's a bit more complicated. You have a few extra rules to follow and checks to do. So image source works by creating mirror images of the source reflected through the walls or the wall planes. So to illustrate this, we'll consider this wall named W1 with the outward normal vector showing. So we're going to reflect in that direction through the wall to get an image source. We call it I1. And then what you need to do is check that this image source sees the receiver through the correct wall. So you basically draw a line between the image source and the receiver. If it passes through the correct wall, then you have a valid image source, and you can reconstruct a first-order reflection. So you can then do this for all the other walls to get all the first-order reflections. And then to get second-order reflections, you reflect those image sources through the other walls. So we'll take I1 reflected through this other wall, W2. We get I12, and then we check for visibility. In this case, it doesn't actually see the receiver through the correct wall, so this image source doesn't contribute to the impulse response between the source and receiver position. So this is what happens in the arbitrary shaped room case. This doesn't happen in the box-shaped room. However, you can figure out that there's a region of the room that would have been visible by this image source. So we could have had a receiver in this region here. So I've drawn this beam through the wall, and this tells me also that this image source sees only this wall, so it tells you which wall to reflect through next. So this is essentially beam tracing. It's a way to accelerate the image source algorithm. So we'll take this image source and reflect it through this wall. We get another image source, I123, and so we check if that one's visible to the receiver. It passes through the correct wall, so then we have to connect it back to I12, check if it passes through the correct wall. So essentially, we're just back tracing this reflection path, and we get a third order reflection path. So in this case, we had a first order image source that generated a second order image source that was invisible, but then the third order one was visible. So this is kind of the intricacies of the arbitrary shaped room case. And if you reflect through the wrong side of a wall, you just stop this kind of generation. So the main issue, of course, with image source is you get this image source tree. So if you have n walls, you then reflect each one through n-1 walls and so on. So it grows exponentially. It's not very practical to carry out to a high order. Typically, people only carry it out to 10 or 20 orders maximum. And it can be accelerated to some extent by beam tracing. However, beam tracing has its own problems. So if a beam hits two different walls, you'll have to split up those beams into multiple beams. So you get another kind of growth, which can be hard to deal with. So the other technique, which doesn't have this exponential growth, but isn't as accurate as ray tracing. So in ray tracing, you just have, you shoot rays in, you sample uniformly or randomly all the directions, and you just shoot rays out, bounce them around the room, and hope that they hit your receiver. Now, if you're just sampling all the directions, you're never going to hit a point-wise receiver. So it makes sense to add some volume to your receiver so that you have any chance of hitting it. So you might have multiple sound paths, like direct sound paths, that hit because your receiver is large, so you have to take that into account. You have to normalize for that. So that's one of the problems with ray tracing. And then you can also think about this as a sound particle method. So if you just imagine these dots propagating along the rays at the speed of sound, they're sound particles. And this has nothing to do with wave-particle duality. It's just an abstraction of waves. Okay. So if you take enough of these rays or sound particles, you can kind of reconstruct a geometric solution, the limit of what you can do with classic geometrical acoustics. So in this case, we can actually see defined wave fronts. So I've just, these are just dots, but they're so closely packed together you can't see between them. But what you can see is there's some discontinuities in the wave fronts, particularly when the wave hits this corner. And that's actually where you get diffraction. So you can look at the wave solution and see that the diffraction kind of continues the wave front here and here. So that's another way to define diffraction, is really it's a discontinuity in the visibility of image sources. So yeah, that's pretty much it. I mean, geometric acoustics, this shows it's just everything minus diffraction, or at least the classic geometrical acoustics. And if you follow along, you'll see that there might be certain parts of the room which just don't get any sound, and that's mostly due to diffraction. So diffraction really fills in the holes in the room and fills in the holes in the impulse response. Okay, now we'll listen to an example of classic geometric acoustics. So I've got a complicated concert hall here with a few 100,000 surfaces, and we're going to shoot out some rays, let them bounce around, and collect them at an impulse, at a position, and listen to the impulse response. So this is just a visualization of what I've done. That's shooting 500 particles, but I'm going to shoot many more. So this is what you get if you have a receiver at the back of the room that's about the size of a head. So I've shot 100,000 rays, and you can see that you end up with a very sparse impulse response. And if you listen to it, sorry. Okay, so it doesn't sound that great. If you increase the number of rays to 1 million, you get something a bit more full, but you can see in the late reverb it's still very sparse, and that's ultimately because it gets harder and harder to fill up the late reverb with these rays because they just kind of diverge over time. 10 million rays, start to get something better, and then 100 million rays. So that sounds okay, I think. And you can keep going, obviously. So you can, of course, kind of complete geometrical acoustics by adding in diffraction. And I'll explain how you would and then what some of the problems are with this. So essentially what you need to do is introduce secondary sources at all the corners or edges or discontinuities of material where you would expect diffraction to happen. And then so here we'll just focus on this interior corner. So I've just got this kind of receiver here. And you have to treat it like another receiver in your room and shoot out rays or do image sources. And whenever it's hit, you have to shoot out more rays from that position to make up for the diffracted wave. And then those will bounce around and get hit again, and you shoot out more rays. So you can imagine there's going to be this exponential growth of diffracted rays or diffracted image sources. So that's the first problem. So you're going to have to deal with that growth somehow. You might have to identify which paths are most important and just focus on those. But the other problem is that you need to apply some frequency-dependent amplitude to those rays. You can't just treat them as impulses anymore because they're going to have some, filtering effect due to diffraction. And this ultimately requires analytic solutions to the wave equation for these diffraction cases, of which we don't really have enough realistic cases to work with. So what we do have at the moment are rigid edges that are infinite in length or finite in length. So that means basically two rigid surfaces meeting at an edge. But you're always going to have some impedance on the walls, and you're also going to need to kind of join that edge with two other planes. So we don't really have anything that's useful in practice. So ultimately, you're going to have to, it's going to always be some approximation until we get more solutions. So over time, people have developed ways to handle some parts of diffraction in room acoustics, such as scattering and diffuse reflections. So if we look at what happens here with just pure specular reflections, the classic geometrical acoustic solution, you see this kind of breakup of waves. It's not filling in the holes. There's a lot of diffraction that's missing. So this is the wave solution you can compare, and it's just, it's not suitable. So sometime in the 80s and 90s, people started extending classical geometric acoustics to include scattering and diffuse reflections. And the idea that most people use is as follows. So if you have some rough wall, you first of all recharacterize it by something flat, which is convenient because that means you have less surfaces to account for. And you assume that the wave is going to hit and some part is specular and some other part is non-specular, which is fine. The problem is coming up with the non-specular part. So you just characterize this by some coefficient, which might describe how the rays spread out uniformly. So that's called the diffusion coefficient, or it might scatter in some particular direction. And essentially what you do is you then shoot out some non-specular rays. So you might shoot out multiple rays, but then that's going to explode, so you don't want to do that. So typically what people do is they just perturb the specular ray by some random angle. Or they might assume that the material is diffuse and that some part of the diffuse reflection is going to go right back to the receiver. So this algorithm's known as diffuse rain, or you might see it as ray radiosity. And it's an efficient way to use rays to build up the late reverb. Whether it's valid or correct is going to depend on how diffuse the room is and how diffuse the materials are. But if you do that, every single ray will contribute to your impulse response. So this is what it looks like when we introduce scattering. So now I've got a flat room, and at the two top and bottom walls, I'm going to apply some scattering and in varying amounts. So essentially, these sound particles hit, and they kind of scatter off in somewhat random directions. So at this point, I'm increasing the scattering. And here, they're just basically going off in random directions. So you could compare that to a wave-based simulation, and you could, maybe argue that it's reproducing the diffusion a bit. But if you really compare these, you'll see that, there are some fine features here which just aren't reproduced at all. So it ultimately depends on whether that is audible or not. And so if you're going to introduce scattering and diffusion, that means you have to run your simulations over multiple frequency bands because there's going to be a different amount of scattering at different frequencies. The main problem with this that I see is that it really departs from any unique solution. So you'll get different implementations of scattering and diffusion, and they'll all give you different results. And these days, there's a lot of geometric acoustics simulation platforms. And for the same input data, they might give wildly different results. And that's ultimately a result of how people interpret this stuff. Because the classic geometrical acoustics will converge to one solution. But this stuff, there's a lot of room for interpretation. So this is how it would look in a more complicated scenario. Up top, so this is a cross-section of a concert hall. We have seats here, which will cause some scattering. There'll be a lot of diffraction due to all these non-convex parts. But here in this geometric acoustic simulation, I've removed the seats, which is typically what people do. And they introduce an equivalent scattering area where you just apply some scattering coefficient. So this is what the scattering would look like in the wave simulation. And this is kind of what you're doing in the geometric acoustics. So here you can see that the particles scatter, maybe simulating something like that. But there's still a lot of diffraction, which is missing. So it remains to be seen if this is valid. It's going to be a kind of case-by-case thing. But that's what's going on. So this is in a cathedral now. So this is a cross-section of a cathedral. I have a wave solution up here. This is with scattering, and this is without scattering, geometric acoustics. So you can see it kind of almost reproduces actually a lot of the diffraction that goes around these pillars. But I mean, you also need to have the correct scale, like the amplitude. It's not just the directions that they go in that's important. So that's classical geometric acoustics, and this is modern geometrical acoustics. So to kind of summarize about geometrical acoustics, so fundamentally it's based on Fermat's principle. It's a high-frequency approximation. Diffraction is missing in the classic geometrical acoustics by definition. You can add it in, which can get complicated. And modern extensions have been developed to include scattering and diffuse coefficients. So they might work. They might make up for some missing diffraction at the walls. Now, the advantage of geometrical acoustics, of course, is they can be computationally cheap. So they're very flexible. You can build an impulse response with any number of rays that you want. You can just shoot out 6 rays, 10 rays, 10,000. You can call it geometrical acoustics. And you can choose how many octave bands you want to do. So there's a lot of flexibility, which makes it very good for real-time applications. But there are those fundamental limitations which are difficult to overcome. So that brings me to the wave-based methods. So wave-based methods are a lot more general. They aim to directly solve the 3D wave equation or the associated first-order system or some generalization of these equations. So here we have the 3D wave equation in terms of pressure. You can rewrite it in terms of an acoustic velocity potential, which is just the pressure, kind of one derivative down in time. Or you can rewrite this as a first-order system in terms of pressure and vector velocity, particle velocity. So we aim to directly solve these equations, or I'll show you some extensions shortly. So in theory, it's physically valid for all frequencies because we're just simulating the physics as best as we know them. And you don't need to build in any diffuse or statistical assumptions. So that's the kind of nice thing, is you don't make any assumptions about the nature of the sound field, except that it's just governed by linear acoustics. And as opposed to geometric acoustic simulations in practice, a wave-based method will inherently find all of the sound propagation paths. So this, of course, comes at a cost. But in geometric acoustics, you will only find, a subset of all the propagation paths. But most importantly, you get all forms of diffraction. So everything that I've been showing you has been due to kind of wave simulation. So that's all generated with a wave-based method. And you have multiple choices of methods. So classic numerical methods, finite difference, finite element, finite volume, and so on. The nice thing is they all converge to the same solution for a given input data. So there's a reliability built into this way of doing things. So this is a simple example of a 3D wave simulation. You're looking at sound waves in a box. you can see the spherical wave propagation bouncing off. And really, to get to an impulse response, you just read out the pressure at some point in the room. So here we're reading it out at this black point here. So this isn't an impulse, but just replace the source with a Dirac and you get your impulse response. So that's how it works. So how do we generate these kinds of simulations? So I'll walk through a basic derivation of an FDTD method, so finite difference time domain, because it's conceptually the simplest type of wave-based method, and it's probably one that most people are familiar with. So for simplicity, we'll consider the 2D wave equation. So here, U is our variable of interest, so that could be acoustic velocity potential or the pressure. And the idea is you just replace your partial differential operators with finite difference operators. So we can take, for example, this second order derivative with respect to the x direction, and we can get an approximation with 3 points. So you just take the value of your field at a point to the right and a point to the left, take 1 minus 2 of this, plus 1 of this, and divide by the spatial step squared. So that's an approximation to that derivative. You can do that in the y direction as well, and you can do that in space. So really, these are all kind of the same approximation, just on different parts of the field. And so you just sub those back into your equation, and then you get a finite difference equation. So this finite difference equation represents an approximation to the wave equation, the 2D wave equation. The next thing to do is you replace your continuous function with a grid function. So the grid function, you define it as an approximation to your continuous solution at discrete sample points in space and in time. So here we have this u, lx, ly, and it's got a time index n, and it's basically, you can see it as samples in space and time of the continuous solution, or an approximation to the continuous solution. And then you substitute that into your finite difference equation, so replace those terms, and you end up with a finite difference scheme. Now, I've rearranged the terms here a bit, and I'll explain why shortly. But the important thing to point out for now is this constant lambda, which is not to be confused with the wavelength. It's known as the Courant number in the context of finite difference schemes. And it's a dimensionless grid ratio between time and space, and it really is quite important for the operation of the scheme. And I should mention, I'll mention this after. So here's our finite difference scheme again. And we can view it as a stencil operation in time and in space. So here we have grid points in space, so along space is along the horizontal, and time is the vertical. And so what we're doing is we're solving for the future value at the grid point Lx, Ly, so that's time step n plus 1, using the previous values, so at time step n and time step n minus 1. And including the neighbors in space at time step n. So there's 4 neighbors in space. And because it looks back 2 steps in time, we call this a 2-step scheme. And you start this whole process with 2 known values. So the first 2 time steps, 0 and 1, you'll have them from initial conditions, and then you just kind of iterate forward in time, leapfrogging in time. So it operates as a time recursion. And I should point out, because a lot of us learn these methods in a different framework, if you take the Courant number here to be 1, so the Courant number squared, if you take it to be 1/2, you get this number, and this will cancel out. And you end up with something which is known as a digital waveguide algorithm, or digital waveguide mesh, sorry. So that's an extension of the 1D digital waveguide algorithm. So that's kind of a way that a lot of us have learned these schemes. So finite difference is just a more general way to describe it, a bit more easier to work with. Now, if we want to extend this to 3 spatial dimensions, we simply add the z coordinate. So here, this is our spatial grid now in 3 dimensions. So the vertical is now the z direction, our spatial step. And this is what the scheme looks like. So I can't illustrate both time and space, but it's essentially this equation. So we're taking a sum over 6 spatial neighbors now instead of 4. So now you have a -6 in there. And then this remains the same. So the next question is, how do we choose h and k? So the grid spacing and the time step. So this is really important. You can start by choosing either one. So I'll explain how to choose the grid spacing first. So initially, you'll choose the grid spacing based on the frequencies of interest. So if you have some F max in hertz, so say 4 kilohertz, 20 kilohertz, by sampling considerations on a 3D Cartesian grid, you'll get a minimum grid spacing that you need to represent those frequencies or those wave numbers. So that's Hmin. So you need to choose your grid spacing smaller than Hmin. How much smaller? Well, you don't want to go too small because the memory costs scale with the inverse third power of the grid spacing. So if you halve the grid spacing, you're using 8 times more memory. And yeah, it follows, this is probably, that the memory cost will scale with the cube of the frequency as well, frequency of interest. Now, if you apply sampling theory to the time step as well, you would get something similar, 2 points per period. So k less than 2 times f max, or 1 over 2 f max. However, there's another restriction on the time step you have to consider for numerical stability. So for stability, typically what you need is the time step less than some maximum Courant number times the grid spacing divided by the speed of sound. Or put another way, you need to choose your Courant number less than some maximum value. So you determine that by some stability analysis. I won't go through a stability analysis here. I'll just tell you that for this basic 3D scheme, that number is square root of 1 over 3, so about 0.57, which means if we were to choose the minimum spatial step, for stability, we would need to choose our sample rate, so that's 1 over the time step, equal to nearly 3.5 times the maximum frequency of interest. So it's much more restrictive than simply the Nyquist sampling criterion. So if you're designing these schemes, you might want to strive for lambda max to be greater than 1, so that you can choose lambda to be 1, which would allow you to get your sample rate equal to 2 times f max, which is kind of the bare minimum you need in time. So this is what happens if you don't adhere to the numerical stability condition. So on the left, we're going to have a scheme that's stable, and on the right, one that's unstable. And we're just going very slightly above the stability condition. So what you get is very quickly the onset of exponential growth. So that tells you did something wrong. And of course, you don't want to listen to that, with headphones at least. Numerical dispersion is another problem. This is essentially approximation error, which you kind of view in the frequency domain. It's essentially a frequency warping, so wave numbers map to the wrong temporal frequencies. Another way you can see it is that you have a frequency-dependent wave speed. So in the wave equation, all frequencies, or plane waves of all frequencies, should travel at the same speed, the speed of sound. But in a finite difference scheme, you get a variation in wave speeds. So this is showing the error in the phase velocity of different spatial frequencies, so wave numbers. So these are the ones that we can represent on a grid going from 0 to pi, well, in 2 dimensions. And it's just this region that's kind of, within the 1 or 2% error criterion. So with the basic scheme, you don't really have much to work with. You might be able to keep all these frequencies. Whether you can hear that or not it's a bit of an open question. But generally, you'll probably have to choose the spatial step to be much smaller than Hmin. So if we take, for example, the simple scheme, this is going to be the same problem with different grid resolutions. So here, with 2 points per wavelength, the minimum, 4 points per wavelength, and 8 points per wavelength. So this is rubbish, basically. This is a bit better. You can start to see the waves propagate. And here, this one's pretty good. But really, the question is whether we can hear these dispersive effects or not. And so we did study this a bit. And what I have here is 2 signals. So this is basically a band-limited impulse, and this is a dispersed impulse. And these 2 signals sound the same to our ears. So they both sound like clicks, according to these listening tests that we did. So there is a lot of dispersion, or at least some dispersion that you can tolerate. So it's not enough to just, for it to be visually accurate. Okay, boundary conditions. So ultimately, you're going to be dealing with a room with walls, and you'll have your spatial neighbors eventually will reach outside of the domain where the problem is not defined, and you can't know that value. So we call these ghost points. So in this case, we have a point next to the boundary, and one neighbor is falling outside. So you have to get rid of this ghost point from your update equation. The way you do that is you introduce a boundary condition. So there's various boundary conditions you can choose. Here I've chosen a frequency-independent impedance boundary condition. So I've written it in terms of an admittance, just for convenience, which is 1 over the impedance. And it gives you a reflection coefficient, which for a plane wave depends on the angle of propagation, or the angle of incidence. So now what you do is you just replace those differential operators with finite difference operators again. So for the spatial one, we have a couple choices. This one uses these 2 points, so it's the difference between these 2 points. And this one is a bit, it's a longer step. It's a distance between these 2 points. So you could use either one. You could do the same thing in time, so you could look backwards in time. So this one takes the present value and the previous value. This one looks forwards and backwards in time. So you have to choose the right combination, both for accuracy and also for stability. So essentially, you'll mix and match. So here I've chosen the non-centered, this one in space and the centered one in time. I've rearranged the equation to isolate the ghost point. You can sub that back into your finite difference update and kind of get an explicit update for this point. So if you make the wrong choice, you end up with stability. So you can have the stability condition over the interior. You can respect that condition, but still end up with some growth at the boundaries. So this is what happens if you make the wrong choice. It just blows up as soon as it hits the boundary. So you can see here, that's the readout. Sometimes that instability is not so obvious. In this case, I've rotated the box slightly to expose some staircasing issues with a regular grid. And I've chosen boundary conditions that are stable when the box is unrotated. So there are different boundary conditions, both stable when the box is unrotated, but when you rotate the box, you expose some problems. So on the left, we have something that's stable. There's some decay you can see. And in this case, you see it's actually growing. So it's a very slow growth. It's actually an exponential growth, but it's just very slow. So eventually it will take off. So you have to kind of wait long enough to see that effect. And so the way to get around this is really to design your scheme so that you can prove that it's going to be stable under any of these kinds of rotations. Okay, there's other time-stepping wave-based methods you can choose. So there's finite element. Very briefly, you project your solution onto some local basis functions and then solve for weighting coefficients, which allow you to reconstruct the solution. You have finite volume. In this case, you apply Gauss's theorem or the divergence theorem to your equations, and then you relate flux passing through adjacent cells of adjacent faces of volumetric cells. And then you have Fourier spectral methods. Essentially, in this case, you transform to the spatial frequency domain, usually over a box and with the fast Fourier transform algorithm. That allows you to differentiate in the frequency domain, which is just a multiplication. So you can do that exactly, and it removes a lot of the numerical dispersion. But the problem is this only works over a box, so you have to kind of break up your room into a bunch of boxes, and you have to treat them all separately and then interface between the boxes, which will bring in some error and maybe some stability issues. Now, all of these methods, they're all volumetric, or they operate in space, in 3D space. They all operate on meshes or grids, and they all adhere to the same sampling considerations as finite difference time domains. So they all have this scaling with the frequency, with the maximum frequency of interest, the cube of that. And that really is, it might seem like it's very expensive, but it's actually a natural scaling because it really is telling you how many modes are in the room or how much information is in the room in the kind of acoustic field. And then So if you look at you can write out the storage density for all these, the memory storage density for all these methods as follows. So here we have some constant which is telling you how many variables you need to store per point. The minimum is 2 because it's a second order equation in time. And then you have this sigma, which is an oversampling factor. So the points per wavelength is 2 times sigma. So you have a scaling in the cube of sigma as well. You can also look at the amount of computation you need to do per point, both in space and in time. So now this is a density in kind of 4 dimensions, space-time. So we have a number of flops, floating point operations, or flop instructions if you want, per point. And now it scales to the 4th power in sigma and the frequency of interest because we've added in time, essentially. And you also have this Courant number sitting there. So essentially, you need to consider all of these numbers if you're going to choose a wave-based method or compare wave-based methods. Typically, people focus on this one, or the number of points per wavelength. But you know, in general, as you're allowed to reduce the number of points per wavelength, the amount of operation you do per point, the amount of operations you do per point, or the amount of storage you might need per point will increase. So there's kind of this trade-off. It's always going to be there. There's other things you might consider. So parallel implementations help speed up these simulations quite a bit. So it helps if the algorithm is parallelizable, and if a lot of the algorithm is parallelizable. You might consider how well the algorithm works on the computers that are available at the time. So multi-core CPUs and GPUs, they have their own bottlenecks, specs that might limit, you know, the use of your simulation. And then there might be some setup costs as well. So you might need to do some meshing or some block partitioning for those block-based methods. That might take a lot of time, sometimes maybe even longer than the simulation itself. And then, of course, scaling it up, that's a consideration. How easily can you scale it up? Is it just, you know, changing a few lines of codes, or is it rewriting everything for a different platform? And then there's the theoretical issues, which are also practical. So numerical stability is the most important thing if you're going to use it in practice. Otherwise, you'll get that explosive growth. It's unpredictable. It's going to ruin your ears. You need to be able to do impedance boundaries. You can't do much with room acoustics without some sort of absorption at the walls. And it should be frequency dependent as well. And then doing things beyond boxes, so complicated room geometries if you want something more interesting. Typically, these features are also hard to get when you have a low number of points per wavelength. So it's another trade-off with this sigma parameter. So, I mean, there's a lot of things to consider. There's a lot of different wave-based methods, and it's very hard to say if any single one is best. Okay, so now I'll talk about, for kind of the rest of the talk, developments with respect to finite difference time domain methods. So I'll go over some of these topics. Hopefully I'll have time for this. Air absorption, modeling frequency-dependent wall materials, modeling complicated geometries, improving numerical dispersion through high-order accurate schemes and optimized schemes. And then at the end, I'll place some oralizations from large-scale simulations. So air absorption. So far I've been talking about the 3D wave equation. The 3D wave equation is actually not sufficient for room acoustics because it doesn't describe air absorption or sound wave dissipation in air. So the wave equation describes lossless wave propagation. But in reality, we have some air absorption effects due to viscothermal and relaxation processes. So this is typically what you have. As a function of frequency, you have some loss, and it usually follows this power law. So this line is classic air absorption. It's given by Stokes' equation, which is just an extension of the wave equation. So now we have an extra term, which is a combination of a time derivative and the Laplacian. And then these extra things, these are relaxation effects. So in this region, so obviously there's a limit of human hearing somewhere around here. And then at some point, this dissipation isn't going to be so important. It actually turns out for indoor conditions, so 20 degrees Celsius, 40 to 60% relative humidity, you end up with the important parts are really linear and following a power law. So it works pretty well to just consider this as a kind of shifting of the classical air absorption. So Stokes' equation allows you to model that. And then you can just, so this parameter, by the way, it's very small. So 10 to the minus 6 meters, it's a length. But it is very important over time. So you can build a basic finite difference scheme for this. Now we have some extra parameters. But the main thing is we do this stencil operation over 2 different time steps, not just one. So that adds to the cost a bit. And you need to store 1 extra value. So now you need 3 variables to store per point. And the stability condition changes as well. So it's a small change because this is a small number. But if you don't adhere to that, it will blow up. And this one, when alpha equals to 0, you have the regular wave equation. This reduces to what I showed you before. So this is what it would sound like in a room. This is a small studio space, about 300 cubic meters. This is simulating up to 16 kilohertz, the lossless wave equation. So we have an impulse response. This is the blue curve here. So you can hear in the high frequencies it doesn't decay properly, and you can see that here. This is what it looks like when you add in air absorption. So a lot better. So you really need that to get anything realistic out of these wave-based simulations. Okay, frequency-dependent boundary conditions. So typically, frequency dependencies in room acoustic simulations, they're treated using multi-band approaches. So you might do your simulation over different octave bands, third octave bands, and then recombine everything using octave band filters. In a wave-based setting, this requires multiple simulations, which can be at different grid resolutions because the frequency of interest will change in each octave band. That has its own problems. You might get some spatial errors due to the fact that your grid spacing is changing, so your source and receiver positions will change slightly. To get around that, you could just run multiple simulations at the same grid resolution, but that's obviously highly inefficient. So running 8 or 10 simulations instead of 1. There are ways you can get around this. You can just model frequency-dependent boundary conditions. So there's a few ways to do it. One approach is to model what's happening at the boundaries as a parallel set of series RLC circuits. So these all have some resonance. Each branch has a resonance. And you need to choose these parameters so that they're non-negative for the whole thing to remain stable. And ultimately, you're going to fit this circuit network to some absorption data or some complex impedance. So in here, I'm just running a greedy optimization fitting this circuit network. So this black line is the frequency-dependent absorption or reflection coefficient. So eventually, it kind of settles on something. And then you can model that directly in the scheme. Staircase boundary conditions. So I showed you an example where I rotated the box and it exposed some instabilities, but there's another problem with staircasing effects. So let's consider a rectangular box with loss at opposing faces, so rigid everywhere else. And in this case, you can actually calculate an analytic solution for a certain family of modes, the ones that vary along that direction between the lossy faces. And that solution, of course, shouldn't change if you rotate the box. But in the finite difference setting, you get very different results based on how you rotate your box. So you can see these staircasing effects when you rotate the box and you fill it up with these kind of regular cubic cells. So that's kind of a volumetric way of seeing finite difference. Now, if you run these simulations to the limit of small grid spacings or high sample rates, what you see is that the modal frequencies converge to the correct results. So that's kind of expected because those have to do with the volume of the room mostly, and the volume of this kind of staircase room will converge to the volume of the box in the limit. So that's kind of a known result. It's also been known for a long time that the surface area of that staircase box or that staircased shape will not converge to the surface area of the box. And what happens is if you look at the decay times of those modes, you'll find that those also won't converge. And that's related to the amount of absorption that you have at the walls, which is related to the surface area as well. And this is even the case when you have very small amounts of dispersion. So it's not due to dispersion. It's really just due to the ability to not be able to not approximate the surface area properly. So a way to get around this, or to improve the approximation, is to take your finite difference scheme and think about it in a more general way. So finite volume is you can think about it as a generalization of some finite difference schemes. So in this case, our stencil now is encapsulated in these 7 cubes. So each point, is at the center of some cubic volume. And if you derive a finite volume update from this, you can actually get at the same thing as your finite difference update. So then you can apply it to complicated room geometries and see what happens. So in this case, we have a kind of theater-shaped room. This is a staircase geometry. And this is what a finite volume kind of approach might be. So you can fill it up with cells that are somewhat like cubes, but adhere to the geometry. And the idea here is not to have a completely unstructured grid or a grid where all the cells change. You just want to have them change near the boundary so that you don't have too much extra memory storage, because you're going to have to store the volume of these cells and surface areas and that kind of stuff. So this is one. It's an approach called the locally irregular mesh or grid. So that's a way to extend it to large rooms. So in this case, you can see here the interior cells are all cubes, but then at the boundaries they change slightly. So that's the idea. So if we go back to that problem, we find that, well, with the modal frequencies now with fitted cells, you get a much better approximation. So that helps. But most importantly, you get the T60s, or the decay times, actually correctly approximated. So this is really important for room acoustic simulations, of course. There's more than that. So okay, first of all, you can combine this finite volume stuff with the frequency-dependent boundary conditions that I showed you before. And if you look at a general problem, so this theater again, here what I'm showing you is the response at some point in this room. And what you're seeing are 6 different simulations. So the responses from 6 different simulations overlaid on top of each other. And essentially you see over time there's a big amount of incoherence. You're not getting one result, you're getting multiple results. You can't really be sure which one's correct. If you now do the fitted approximation, those 6 simulations, so that's, I'm using 2 different cell types and 3 different rotations. And so they all return the same response essentially. So that's telling you that you're kind of converging to the unique underlying solution of the problem. So that's really useful as a reliability tool, I guess. So with all these complicated boundary conditions and fitted cells, you can still do numerical stability. The way to do it is, or at least one way, is to write your scheme in terms of energy. So you have some discrete energy, which is an analog of the continuous energy, and you can track this energy throughout your scheme, and you can bound it. You just have to show that it's positive, and you can show that it's not growing, essentially. So here we're looking at different energy terms in the simulation, tracking them, and the total energy is here conserved to 15 decimal places. So this is the variation, the normalized variation. It's on the order of machine precision. Ultimately, you just get variations that are machine epsilon steps. Okay, so this, I'll go through this quickly. This is high order scheme. So if you increase the stencil size beyond 7 points and choose your coefficients properly, you can get better approximations at lower, or the same approximation accuracy at different grid resolutions. So this is a 4th order accurate scheme using 4.5 or nearly 4.5 points per wavelength. This one's been optimized a bit so we can use a bit lower grid resolution and trading off a bit of accuracy. Okay, now I'll play the oralizations. So yeah, so far I've just shown you animations. It's not just for animations. You can actually make sounds out of this. So I'll play some dry sounds first. So this is a cello sample. And so now I'm going to play the convolved version with the impulse response that was generated from an FDTD simulation. And this is actually all the way up to 20 kilohertz, all wave simulation. So the source is here. We were listening from this receiver position. We'll listen now from this receiver position. So you can't really hear any dispersion in this convolved audio, but there is dispersion. And it's really just because I've chosen a pitch sound. But if I choose something with a bit more transients, you'll start to hear the dispersion. So this is the dry audio I'll feed in now. And from the first receiver position, which is about 10 meters away, we get this. So you might hear some kind of chirps on those transients. It gets worse when you go at a farther distance away because this is kind of a phase delay or a phase artifact, so it picks up with distance. Can you hear that? So yeah, for higher frequencies, you might have to increase your grid resolution, or you might decide to do some sort of hybrid geometric acoustics and wave-based things. So here I'm just using crossover filters at 4 kilohertz, so the low frequency that's with waves, and the high frequencies with the impulse response that I played for you before, the one with 100 million rays. So now the castanets sound like this. So you don't have any of that dispersion anymore. And at the back. And the cello will sound a bit better too. Okay, one last example. This one's a large cathedral, 41,000 cubic meters. So that last one was 14,000 cubic meters. So obviously this scales with the volume. So a bigger volume is going to mean you can do, you're not going to be able to go as high in the frequency range. And this is also a more reverberant space. So this is the dry audio that I'm going to feed in. And so now we're going to listen to it played from this point, so within the choir, and then listening just outside at a distance of about 20 meters. So this is like 100 meters in length. Okay, so that was waves up to 3 kilohertz in that case, and then the geometric acoustic simulation with tons of rays. Okay, so should be able to just make some final remarks. So modern geometrical acoustic simulations, they're fast, ultimately limited in theory to high frequencies or places where you don't have diffraction or diffraction is not very pronounced. Wave-based methods, they're complete in theory, but expensive in practice. However, they're not impossible to run. So for a long time, people have said, they're just completely impractical. But today, they are practical or possible, well into the mid and high frequencies, provided that you have enough computing power. So you don't need a supercomputer. You need a few GPUs or one GPU. But we're really only scratching the surface of oralizations with wave-based methods or even hybrid approaches. So yeah, stay tuned. There's a lot of things I didn't talk about. So for example, binaural audio, directional or volumetric sources, moving listeners, and spatial audio capture and reproduction. So all these things, you can do them in a wave-based setting. You basically just have to discretize the physics that describes those effects. So I didn't have time to talk about all of those things, but maybe a future talk. And that's it.
Thanks. One or two questions?
Yes, I was just wondering if you guys have been able to validate these methods, like if you had a CAD model of a particular space and you have access to being able to record in that same space, if you've been able to compare impulse responses, and if you can comment on any qualitative or quantitative differences between the real and simulated.
So we haven't yet, but we're kind of in the process of doing that. As you might know, there's a lot of problems with getting just a good model of the room to simulate from. So I don't know if you can really expect it ever to match. It should match in theory if you can get all the input data correctly. You're modeling the physics that makes up the sound, so it should match in theory. But the problem is capturing the geometry to a sufficient resolution and getting the impedance data or the absorption data. So yeah, it's still kind of future work.
How do you evaluate your model is close to the real case?
How do you evaluate that? Well, you might look at objective parameters like T60s or early decay time, that kind of stuff. Or you might just compare the oralizations from a perceptual point of view. I don't really have an answer. But yeah, there's multiple ways to compare. I can't say which one's the best way.
Thomas?
Yes, I was wondering, did you have a source directivity model also in the simulation?
No, in these ones, no. It was all omnidirectional sources. However, if you pay attention to the Wasberg proceedings, Stefan and I wrote a paper on directional sources. So yeah, I mean, you can start to model directional sources as well.
How do you make a fitted model to an arbitrary room?
Good question. That's generally a meshing problem, so there's a lot of, there's probably 50 years of research into meshing. So there's general techniques to do that. There's software you can get, open source software. The question is really, how do you do it in the context of room acoustics to make it, practical for large scale simulation? So we've just kind of come up with some techniques, mostly based on Voronoi grids. But there isn't really a good resource for this kind of stuff because it's kind of, I guess it's kind of new approach of doing things.
What is the grid called? What is the grid called again?
Oh, Voronoi grids.
Oh, Voronoi.
Hey, everyone. Are you able to drop the grid spacing or the time step in the middle of a simulation? So rather than doing repeating the simulation for different frequency bands, doing the whole simulation for each one, can you just do one simulation and drop the spacing or the time step as you go? Is that even possible?
I mean, you would get aliasing effects if you just started removing. You would get aliasing. Maybe you could do it, based on high frequencies are dissipating, and then you can start to use. That's a good. I mean, there's going to be some interpolation issues, stability issues. People do these subgrading techniques, but I never thought about it in that way.
I just figure as high frequencies sort of start disappearing,
that's a good idea.
Late reverb is often run in lower sample rates.
I mean, so I just know there's going to be problems with that, but it doesn't mean it's not possible. So. Yeah, never tried it.
I was actually going to ask kind of a similar question. I don't know if it's possible again or not, but if you were only trying to calculate the impulse response with just at a single point, would that change any of your considerations with how much you'd have to space, knowing that something from farther away you might be able to sample more coarsely and how it affects? I don't know if anything like that has been considered or is worth it.
Yeah, I haven't considered that stuff. The main idea right now is just to try to do it in a very general way. So later on, you could start to, cheat a bit, take some shortcuts.
I have a kind of a two-part question on the boundary conditions. One, I think I had the impression that in the beginning you talked about angle-dependent impedance conditions and the finite difference. Is that actually possible? Because I didn't see in any of your schemes.
Oh yeah, I mean,
angle-dependent impedance?
No, it's not an angle. So I wasn't putting in angle-dependent impedances. If you put in an impedance, you'll get an angle-dependent reflection coefficient. If you had an angle-dependent, some reflection coefficient which didn't adhere to that kind of cosine of this over that, that's going to be a non-locally reactive condition. They are possible to do, yeah. So nobody's really started to do them.
And then the second part is in terms of complex surfaces. If, for example, if you want to do something you don't want to grid up to millimeter precision, then you have to make some approximations on the scattering and on the impedance, and then you're basically falling into the same trap of the geometrical acoustics.
Yeah, I mean, they both have that same problem. So I don't think it means you should just, you know, use one method or the other. I mean, they both share that problem. But yeah, it's kind of, that's future work, is to figure out those issues.
Some more questions? So we once again thank the speaker, Brian Hamilton.